Okay, so last night we talked a little bit about the VRF algorithm in Polkadot. So basically, that stands for Verifiable Random Function. And in the case of Polkadot, it takes three values: a secret key, some random value that's based, as they say, in the hash of the blocks of the previous item or epoch, and a slot number. So it takes some values and it produces two things: a result, which is your random value, and a proof, which is the random value was generated correctly. The result is then compared to the threshold. So let's say there's, if the random value is less than, let's say it's 1 from 100, if it's less than 30, then you can become a validator. In some ways similar to what you see with proof of work. If they come up with the number that's less than the threshold, then they could become a validator or a miner, get the mining credit. So, understanding that, let's look at this. Okay, so we talked about it takes a secret key. Let's look at private versus public keys. Very commonly used. So in one case you have a situation where you're sending data to someone and the public key encrypts it, and then only the person supposed to get it can decrypt it. And that way because the private key is private, no one can steal it and decrypt it along the way. With digital signatures, you sign it privately, but the person supposed to verify can verify it using the public key, and the same thing with authentication. Now, when you get into the VRF algorithms, you have, this is similar to what we're talking about. We had our secret key, we had our values, the various values you put in, and you come up with a random value. Okay, so now let's look at VRF algorithms. Remember we had the secret key, and this alpha can represent the other hashes and other values, and you get some value which is beta, or in this example, I put these two side by side to help understand it better. You put in all this stuff and you get a value. Call it beta, call it y. That's your random value. But remember, it's a random value on a proof, so what do? So they have a proof algorithm. They take, again, the secret key and the value, and they get P or PI, which is your proof. Now, what you can do to prove it, so remember you're going to verify that beta was in fact produced correctly. You have another function, they call it f of skx, here it's called Vrf Proof To Hash. You take that proof and that returns beta. And to prove everything, you have this function should be, if the original beta should equal the same value as if you put pi, or this, pi is the result of proof, if you put this into here, and if they're the same, we know it's good. So you have two factors here. You have the beta, which has to be below a threshold, and you have a proof which is based on various algorithms that, where they take the data, they produce this proof, and then the proof with this proof to hash, or this, let's see, f of sx, should equal the same value when you put the proof in, should equal the same value as what you originally got. So you have one algorithm that generates your random value. You have another pair of algorithms. One generates the proof, and one takes that proof and regenerates the random value. Note what they say here. You can always check it because you're going to have beta and you're going to have pi, and so pi is, there's no, once you're given pi and beta, you can, if you pi, here you have pi you need, and you need beta, because beta equals here, proof to hash. So all you need is beta and pi, and if you put pi into the proof algorithm, then it should give you your random value. However, you cannot determine the secret key, so that allows for the security, because all they're given and all they need to be given is the proof value and the random value, and then there is an algorithm that will calculate whether that proof value is in fact what generated the random value. So hopefully I've made this a little clearer. It is a fairly complex idea, but the whole thing is you've got this value that has to be below the threshold set by the chain, and you need to verify that that value was not fudged, was not hacked. And that's why you have these verifiable random function rather than just your typical, what I showed last night with this typical random number generator. So hopefully this has been helpful. If it is, please give a like, and if you want to see more, please subscribe and ring the bell, and I will see you next time.